Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good day to every one of you. Hope everyone is in very good of health and conditions wherever you are. And then for this session, we will continue with the next chapter, with the next section of in the instrumentation and process control for the topic of PLC, programmable logic controller. So let me just share the screen here. So we are now in the chapter 5, programmable logic controller. Okay, in this chapter we are going to look into four main sub topic, which are inputs and outputs of the PLC. We're going to look into the logic programming symbol, and then we look at ladder diagram programming. And this is which I believe has been assigned to you as a group project, and we will look into several type of PLC example. All right. Okay, the basic schematic or the basic architecture or structure of the PLC system is shown in this figure. This illustration best to explain what is the PLC and where is the PLC in the instrumentation and process control. So basically the PLC is the interface between the input and output of a control system. Okay, the PLC is the one that will instruct or will coordinate, will is the one that will be uh, uh, arrange how the input is going to control the output. Okay, for the input, normally for the PLC we will use sensing device such as switches, and then maybe a sensor. And then for the output, the most commonly used in many cases is actually some sort like a buzzer, like a light, like a motor, and uh, etc. So that we can convey the input from the human, and then so that it could reflect to the output, which normally will be highlighted as the uh, alarm or control of the processing control system. Okay, for the PLC, okay, PLC is the brain. This is the one that we process all the input and to convert into the output, and this is the one that we create the algorithm and how we want the input to be processed. Eh? Of course, when we come to when we talk about logic controller, programmable logic controller, it will involve programming languages such as ladder diagram, sequential logic, FED, structured text, and etc. These are among the popular, and out of these four, the most convenient and the most commonly used and the most easiest for to be implemented is actually the ladder diagram. Okay, why we call it ladder diagram? Because the structure look like a ladder. We will talk about this in the next section. And in fact, I do believe every one of you at this stage have gone through the topic of the ladder diagram or ladder language, because you are completing your group project on this topic. Okay, PLC PLC will involve logic symbol, logic algorithm. Okay, for that we have to know several types of the symbol that commonly used, and in this case there are two representations, which on the right side is the physical representation, while on the right side is actually the PLC representations. Okay, for example, we have a coil. So for physical representation, it'll be like this one, a box with a cross into, and for the PLC model, it will look like this one. And for NO contact, and what is NO? This is actually normally open, and normally O open, normally open switch. Okay, for physical representation, it represented by this one, while on the PLC, it's just like a capacitor. And for NC contact, it's actually normally closed. For NC contact, it'll be like this one. We have the switches and connected by a line here. Similarly to the PLC, we will see the capacitor connected by a line. So these are example of that one. And then for the logic programming symbol, and normally for the PLC, we will use logic booleans. Okay, this is what we call it. These are the main four logic booleans that mostly use, which is AND. We have AND, we have OR, we have NAND, and we have NO. Okay. For the PLC representation, for AND logic, okay, how and when we're going to use AND? Okay, how and when we're going to use AND conditions? Okay, we have a situation in which, both switches need to be open in order for output to turn on, uh, to become high, to become 1. Okay, so in this case, if this one is open, so the output will be not open, I mean remain off. If both of these open, then only the output will be on. Okay, so they are connected in series. Okay, for the OR, so we will have NO switch, NO contact, which are connected in parallel. Okay, it can go this way and it can go this way. Either one will be can be a path for the signal to be transmitted to the output. And we have NAND, we have NC contact or NC switch that is connected in parallel, while no logic is represented by NC. This one NC, normally closed switches that connected in series. Okay, these are the most commonly booleans that been used for the simple instrumentation and process control. And these are the symbol for the PLC that to be used in the ladder diagram. These are the one that to be used depending on objective or specific uh, objective to be achieved. Okay, ladder diagram. Okay, now we come to a ladder diagram programming. Okay, it is a special schematic representation of the hardware, and its connection has to be developed that make combination of hardware and even of sequence description are clear. Okay, so it means that we have a combination of hardware so that it happen in sequence. Okay, say for example, we have L1, L2. Okay, so we want to know, we have NC switch here connected in series with NCB, and then this is the input and this is the output. So the combination of this will determine what will happen and at the output. Okay, so this is the simple ladder diagram, also called as contact symbology. Okay, because it shows here how they are connected and how the contact switches here will decide what will happen to the output. Okay, ladder is means of graphical representation of the logic required in the relay logic system. Okay, we will implement the relay. We will have a switch and latch. Combination of this is what we call as the ladder diagram. Why ladder diagram? Again, it is because if you can see here, the structure of this representation is look like a ladder. This is an example of a complete one. You can see is 1, 2, 3, 4, 5, 6. Okay, we have it look like, quote and quote, look like a ladder. Okay, how we interpret or how we introduce this ladder diagram. Okay, first we will use a combinations of logic, logic programming, and we will use the symbol. Okay, one is the physical symbol and the other one is the PLC symbol. Okay, how we interpret or how we interpret or the ladder diagram is from left to the right and from the top to the bottom. Okay, left to the right and top to the bottom, and then each level, okay, each level is called as rung, rung, rung. This is level, uh, this is rung 1, this is rung 2, and so on and so forth. Okay, so like this one, how we okay, normally input will be on the left side, while the output in term of buzzer, in term of light, and motor, for example, will be on the right side. Okay, input elements and the output element. How we read this one? First, we need to go through rung by rung. Okay, rung 1, rung 2, rung 3, from left to the right. Okay, this is just the introduction, the introduction to the ladder diagram. And if we look here, what happened to this logic circuit, logic booleans, we have none here connected to the N. Okay, try to refer uh, to your basic electronic boolean digital, and then you will see this. Okay, so we have the output, AB. Okay, AB, and then the output is this one. If it is 0 here, 0 here, and then we'll have output is 1. Okay, and we can do the booleans. If 0 is here, 1 is here, this one will be 0. Okay, so I think you should manage yourself how to interpret or how to establish this boolean representations. And this is the truth table, in which you will see the input and then you will know what is the output. All right, so another ladder diagram elements, as I mentioned, it will involve normally relays, motor, light, and switches. Okay, solenoid. Okay, these are normally the output elements that been introduced with the ladder diagram. A simple instrumentation process control will normally involve this one. Okay, so we have several more of the symbol of input device used in ladder diagram. So we have a control relay, we have a switches, NO, normally open, NC, normally close. And we have a timer relay, if you want, we have normally open and normally close as well. We have the R1 represented by timer relay. Okay, this is CR. What is CR? Control relay. Okay, so these are the symbol and these are the PLC representations. Okay, and then we have a motor output, motor M1, M for motor, and then we have solenoid. It's like zigzag shaped. So we have the light R, which is the symbol of light, R represent red. Okay, symbol of output device. This is the symbol of output. This is the symbol of input. Okay, and then for switches, we have several type of switches. As you can see here, we have a momentary action push button. in which you will push this one, and then it will latch for a moment only, I mean for a short while, and then once you release your fingers, and then this switch will open. Okay, we have physical limit in which you can push the switch to a certain limit, and then we have pressure limit, and then we have temperature, we have level limit, we have so many switches here that can be used depending on application. Okay, these are the symbol of switches used in the ladder diagram. These are so-called what we call the most commonly used in the ladder diagram. All right, okay, for we have here a case study 1 and 2, and then I would strongly advise every single of you to look at these animation videos at the provided link here. It will enhance your understanding on how to establish a ladder diagram based on specific operation. We have two, the oil in the vessel, oil level, and then we have bottling on the conveyor belt. Okay, so it is very interesting video. It is a very interesting animations that could definitely will enhance your understanding. Like this one, we have the ladder diagram here. You have a ladder. Okay, rung 1, rung 2, a combination of lots of switches and output here, motor, x1, x2, x3, okay, x1, x0, x2, x3. So each of these have a specific function, and they need to know where to be switched on and off in order to operate the system. Okay, let's just watch this video. Oh, sorry. Okay, maybe I'll just operate from this one.
Hello folks, and welcome to Practical Ninjas. Hello folks,
Okay,
and welcome to Practical Ninjas.
okay, this video is belong to Practical Ninjas in the YouTubes, all right? It's very good videos that can enhance your understanding.
Let us start our video today looking at the setup shown here.
Okay, let me just rephrase what been explained in the video. Okay, so basically we have instrumentation process control. We have a process control. We have a conveyor belt here, and we have a bottle on the conveyor belt, in which this conveyor belt connected into between the machine 1. This is what we call machine 1 and machine 2. And then the conveyor belt will going to the right direction from left to the right, and is coming out from this machine and going out into this machine. Okay, okay, that's two machines. Okay, bottle exit, and then okay, in the case of fault conditions in either machine 1 or 2, okay, and we also have to inputs, okay, information about the status of the machines. Okay, we have two inputs and two outputs. Okay, okay, now we have the conveyor belt and the output here.
The alarm has to go high if any of the machines stop.
Okay, so consider a scenario in which there is a fault conditions. If the fault condition, it will send the signal to this input, and then it will trigger alarm. And what will happen to the conveyor belt? It will stop. Okay, so two inputs. Okay, input 1 and input 2. This one will send a signal to into the two outputs. One is the trigger alarms, and the other one is the conveyor belt and the operations. Okay.
As a all boolean stop.
Okay,
This can be implemented.
Okay, let's just listen to this simple representation. Have a look at the animation so that it's become clear.
As a all Boolean logic. If any and the other quite clear. We have two inputs.
Okay.
If you are new to the channel, press the bell ado, telling us if the machine has stopped or not. There are two outputs to be controlled in this case. The one is
Oh, sorry. Okay. I think probably error. Let me just check. This one. PLC. What is? Okay, this one. This video.
hello folks and welcome to Practical Ninjas. Let us start our video today looking at the setup shown here. The setup consists of two machines connected by a conveyor system. Bottles exit the first machine and enter the second machine as seen here. Automation for the conveyor system needs to be implemented. If any of the two machines
Okay, these are the scenario. We have the scenario machine 1 and 2. We have a conveyor belt. We have a bottle from machine 1 and 2. And the scenario is that if the fault conditions happen in either of these machines, and what will happen to the process control now?
stops due to any reason, the alarm should go high
Okay,
and conveyor belt should also stop.
okay. In this case, what if the for the fault conditions, it will trigger alarm to goes on, and the conveyor belt should be stopped. Okay, that is the output of this one. Okay, how to obtain the fault? The fault is from the input.
We will be trying to implement this logic using PLC in this video.
Okay, this maybe attractive representation of the PLC, in which you can assign this one to be the input and this one to be the output relays. Okay, we have power supply, of course, and these are the one that we will decide the control system to be used for this system.
So, stay tuned until the end of the video to understand how to implement this logic. Don't forget the solution for this case is quite clear. We have two inputs,
All right,
each from the machine,
input 1
telling
and
us
2,
if the
machine 1
machine
and
has
machine 2.
stopped or not.
That's why
There are two outputs to be controlled in this case.
we have
The
two
one is
inputs
alarm
and two
and
outputs.
the other is the conveyor motor. The alarm has to go high if any of the machines stop. This can be implemented as a OR Boolean logic. If any input goes high, output goes high. So basically, we need to implement OR logic in PLC ladder programming. In the previous video, we had implemented AND logic. To implement OR logic, two inputs will be connected in
Okay, remember what I explained to you? The OR logic can be represented by NO, normally open switch, that connected in parallel. Okay, this will be the input and this will be the output. Output is in this case probably the alarm, the buzzer here, the buzzer light here.
parallel in a single rung of the ladder as shown here.
This
We
is
are using NO contacts
okay. This is the single rung, or what we call it as the first rung for this one.
of the inputs in question. At the output of the
Okay, input 1 and input 2. In the diagram before, it says machine 1 and machine 2. This input 1 and 2 coming from the machine 1 and machine
this
2.
rung, we will be connecting the alarm. Let us visualize what happens when any of these machines stop. The NO contacts turn NC even if any input gets activated. This completes the rung and the alarm goes high. Thus, we have implemented the first part of the question.
Okay, now, okay, for this one, we have developed the first rung of this situation in which, based on input 1 and 2, either of these machines is showing, is giving the fault, okay, either of from machine 1 and 2, this will trigger the alarm, okay, this will trigger the alarm. Okay, next, we will prepare for the next rung or the next layer in which this layer, the first rung is actually controlling the output of the light, and then the second rung will try to control what will happen to the conveyor belt. Let's
And
just
also understood
continue.
how to implement OR logic. The second part of the question wants us to stop the conveyor when the alarm goes high. This can be implemented.
Okay, remember the condition is that when alarm goes high, which is the when the light is switched on, this will trigger the conveyor belt to stop. We can actually use the NOT gate. That just this is the NOT gate from NOT booleans.
As a boolean, not logic. To implement this, we will be using the NC contact of alarm as input and the conveyor motor as output. Thus, when the alarm goes high, NC contact turns to NO and cuts off supply to the motor.
All right. So when the alarm goes high, when the alarm is triggered or switch on, the NC normally closed will be in the switch on condition, that will be disrupt the signal to the motor.
This stops the conveyor system. In this manner, we have implemented and solved for the second part of the question and also learned how to implement not apply to the motor. This and also
Okay, so for the overall of this system is actually from input 1 and 2, if the fault happen from either machine 1 or machine 2, this will trigger alarm, right? This will trigger alarm or the light if you want. If the and then we use the NC contact, NC contact. If the NC no, in it is in normally open, normally closed condition, that will trigger the conveyor belt to running. And if it is this one is in high position, this will trigger this one to switch off the conveyor belt. That is the scenario uh, for this situation. Okay, so we will have two rungs operations for this simple control system, right? And then okay, okay, so we have the, oh sorry, it's not responding. uh right, let me just check the notes. Okay, oh sorry, it's hang. Okay, sorry about these technical issues, so we'll just continue. Okay, okay, that is one example of implementing automation for bottling of this drink. And then we have the second case study, which you can refer to these YouTube videos about the water leveling. Sorry, oil level in the vessel. You can go to this link and then you can see the explanation of this one, how to establish this rung, this ladder diagram. Okay, I leave it to you to look into this one, and then probably we'll discuss in the class. Okay, and this is the video just now. All right, so now we come to the simple work. We come to one example here. Okay, prepare the physical and program ladder diagram for the control problems shown in the figure 41. This is figure 41. The global objective is to heat up a liquid to a specified temperature. We're going to heat up this liquid or oil, if you want, to a certain temperature, and keep it with the stirring for 30 minutes. Okay. So the hardware has the following characteristic. Okay, this is given. Okay, we have start push button is NO, stop and NC. We have this one, start push button, NO normally open, stop and NC normally close. And we have NO and NC are available for limit switches as well. So we have a limit switches. Example of the limit switches as example, and the use of limit switches is actually this one. We have level 1 and level 2. Okay, there are limits of this 1 and 2, and whenever the water reach this point, it will pull the limit so that this one will be trigger switch on. And if the oil level goes beyond the lower limit here, uh, and then it will switch on, and that is referred as a limit switches. Okay, the event sequence of this tank is actually, first we fill up the tank. Okay, we fill up the tank, and then we heat up and stir the liquid for 30 minutes, and then empty the tank. Repeat from step 1 till the end. Okay, so we'll fill in the tank and until you come to the full limit, and then we heat up and let it stir for 30 minutes, and then we empty the tank, and this process will be repeated. Okay, let's look. Okay, these are the solutions. The solutions, this is what we call a physical ladder diagram. We have a physical, so you can really see it's a ladder diagram, but it's a physical symbol. So you can see this is NO or NC. This is NO, normally open. This is normally closed switches. Okay, and we have limit, level up, limit switches, and so on. Okay, okay, these are physical ladder diagram. The solution is provided by, okay, you can read through the solutions, you can read through the solution and try to understand. Okay, so basically these are the explanation of for this rung. Okay, figure 42, this is figure 42, show the 6 rung physical ladder diagram. Physical ladder diagram, 6, 1, 2, 3, 4, 5, 6. We have a 6 rung. Okay, rung 2 opens the input valve. Okay, rung 2 open the, provided the output valve is not open until the full level is reached. First it open the input, and then it will rise up, and then where the full level is reached, rung 3. Okay, next stage, rung 3 on the stir. Okay, so we have the stir here, 30 minutes. We have V in, input in and out. We have control relay here, control relay 1, and then okay, rung 3 to operate the stir, and then rung 4 is to operate the timer. timer relay. So this has to be 30 minutes. And then the heater is controlled by rung 5. Rung 5 is control heater. Right? And the rung is energized and de-energized as the temperatures goes, okay, below and above the limit. This is also another control. When the timer times out, the rung is de-energized and the rung 6 is energized to open the valve. And the rung 6 is energized or is switched on to open the valve, so that to allow the fluid to come out from this bottle. So if you can see here, each of single operation here is normally represented by rung. Okay, fill up the tanks will be 1, heat up and then stir, and 30 minutes will be 3 operations here. So we have 1 plus 3 equal to 4, empty the tank equal to 5, and repeat will be 6. So altogether each individual operation will be represented by the rung. So here we allowed uh, that will reflect this physical ladder diagram will reflect the operation of the sequential. Okay, these are the physical ladder diagram versus program ladder diagram, the PLC, the program booleans ladder diagram. So we have the contact here. 01 is indicate here NO start switch, NC stop switch, and it represented by the numbers for convenience, so that we don't really see the text on this one. And this is a more clean structure. They are just the same, physical just showing the symbol, and this one is just denote by the numbers. Try to understand this, and then I will probably ask in the class or during the Q&A session. Okay, the explanation is here, just like I mentioned to you. We have the operation, this one. Okay, the left side will be the input. Okay, the left side will be the input and the right side will be the output, and we are from left to the right and from top to the bottom. They are interconnected to each other. Why see control relay? Control relay because control relay is dependent to other rung. Okay, these are dependent to other rung. Right. Okay, we have the same example. A liquid level is shown in figure Q4C. This one figure, the same figures. Pump will run when the liquid is below. Okay, the condition one. Okay, pump will run when the liquid is below the low level. Okay, low level here. And then LE. Okay, which is LE, okay, low level at empty, and pump will stop when the liquid above the high level. This is the high level. Okay, L up. Initially the tank is empty. Okay, initially the tank is empty. The control system is added. Okay, the control system is added with start push button, the stop push button, and the pump motor starter. Okay, design the ladder diagram of the liquid control level for this process control. Okay, actually the scenario is exactly the same to this one. It is exactly the same to this one. It just a matter the rewrite the sentence is so that is more structured, and the solution is just the same. No, sorry, it's slightly different because this one not involving the elements of heat, stir, and for 30 minutes. Okay, this one, this condition is just fill up the tanks. The motor will pump in water if it is reach low level, and it will stop if it reach the high level. And then okay, initially, okay, it's very simple. I think this can be achieved by only 4 rung. Okay, and then PLC example again, we have minimum and maximum X1, X2. and we have a liquid one and two. We have a motor to stir, and we have the solenoid, and we have start, we have stop, emergency button, start XO, X1, uh, and stop. We have several button here for the control. And then another work example is about mixing a liquid in the vessel and in tank as well. Okay, we have an inlet one, material two. We have the processing procedure inside this one. We have a temperature, we have a level A, level B, and we have the outlet. Okay, more or less about the fuel or fluid level is about the same. How many rounds will this one require is depend to the operation that is needed. Sometimes may as minimum as two or three or as one, for example, and then sometimes might require up to 10 or more. Right, it's depend to the operation that will be executed. Okay, as for exercise, okay, design the physical ladder diagram and design the program ladder diagram of the liquid process in example 1 and 2. Okay, try to do by yourself, even though you have, I do believe, maybe most of you have worked out on this one through the group project. That is very good, and you have done a case study for each individual cases. Maybe you are now very comfortable with the ladder diagram, but you can try to do this exercise by yourself so that you know where and which, how to proceed, how to construct this ladder diagram. Okay, with that, I think we come to the end of this session for the PLC. So hopefully you should be able to grab a gist of this topic of this chapter, programmable logic controller. We are looking at the input output, how to do the programming and ladder diagram, the combinations, and some work example. All right. Okay. Thank you. I think I'll just stop here, and then I shall see you next in the next class during the Q&A session. You may ask me whatever that you confuse you, and we can discuss in the class. All right. Thank you very much, and have a good day. Okay. Assalamualaikum warahmatullahi wabarakatuh. Okay. I'll just stop the recording.